Hello, everyone. This kind of reminds me to my own introduction to my own YouTube channel every time I do this. But hello, everyone. Welcome to the learning platform of United Motorsports Academy. And we are kicking off with a free webinar in collaboration with Formula Bharat, which is the FSA of India. And we have our own competition for students and universities in the name of Formula Bharat, and United Motorsports Academy is the knowledge partners for students, so that students can uplift their game and make better cars and make the competition a success. But coming to UMA, UMA's core value is to make motorsport education accessible and affordable to everyone. And in this context, we are kicking off with a free webinar delivered by Mr. Punith himself. Now, before I start on to introducing Punith and how how webinars work, I wanna throw things off a little bit because as a kid, I think for me the biggest question was how could how do F1 teams actually are able to replicate the complexities of a non-linear environment like the track in developing the car. So in the wind tunnel in CFD, and during my time at Red Bull Racing, I think I was able to see that firsthand. However, I was not very much involved. I was very involved in the aero development processes, but not in the wind tunnel. So when I started having a chat, when I found Punith on my LinkedIn sphere, and I started having a chat with him, it actually kind of blew my mind on details that I had missed out during my time while I was there. And I said, Punith, we have to get you on a webinar, and people need to know this if you're okay with it. And Punith, with his enthusiastic nature of sharing knowledge, was willing to come on board onto this webinar and share what he's going to share with you guys. So this webinar is going to be extremely um, it's going to be a webinar so that we address all the entire audience, where we try to ask certain questions and we try to demystify some of the usual questions as to how people replicate racetrack conditions on wind tunnels. So before jumping into the details, I'll just give you a quick introduction to Punith. Um, Punith has been working in the field of motorsports for the last 15 to 20 years. And he's worked with we started his career with McLaren, working with them in the automotive domain, um, specifically in the F1 industry, and then he went on to Toro Rosso, to Williams, and he's also worked as a front wing, or not a front wing, a front car manager at Sauber, which is effectively my boss when I was working at Red Bull Racing. So in a very funny way, when I first met Punith, I said, I wish I found you when I was a kid, when I was younger, so that I could take some advice from him. Because I felt like in lots of ways, I was one of the very few people who had made it from India into an aerodynamics division, into F1, like born and brought up and reached that target. But when I met him, I realized, shit, there's already somebody who's been there and done that and progressed much more in a career than me, to be honest. So without throwing out away all the formal introduction, I just say the stage is yours, Puneet. Let's learn from you, and we're going to keep this conversation very interactive, where wherever I feel like there's a buzzing question that might address the audience, I'll just pitch in, and wherever not, we'll let you go ahead with your presentation. So stage is yours. Let's go.
Yeah, so before I begin, first of all, I would like to apologize. This was supposed to happen last weekend. I know a lot of you would have planned for it last weekend. I fell ill. I don't think you would have understood anything I said because I had the flu and it was very congested. So I've recovered enough to, I'm really happy that I've recovered enough to do this weekend. So I'm really looking forward to this. The second thing I want to say is Shubham and UMA, they've created something really, really interesting and cool here. And I'm really, really happy to be associated and get this started. So
Yeah.
when we were talking about this webinar, Shubham, so you were really interested in me before talking about anything technical, and we'll get to it because Formula One is very technical. We talked about just having a chat about my career because in the end there are lots of engineers on this webinar, aspiring motorsport engineers, and that was one of the things that we said we'll do. So my career path, I've spent about 10 years in Formula One, specifically at Williams, Alfa Romeo in Switzerland, and Alpha Tauri in the UK. But before that, before F1, I actually spent a good few years in the automotive industry. I worked at McLaren, at Williams Advanced Engineering, but my career really started at a CFD company called EXA in the US. Just a little anecdote there. None of this would have actually happened if not for a bit of a lucky break. As a lot of students find themselves in this kind of situation, I finished my master's in the US and I'm looking for a job. Visa sponsorship is an issue everywhere, and under pressure to find a job, I almost accepted a job from a pump manufacturing company. So none of this would have ever happened. So that was my that I would have gone down that road. But the day before I accepted that job, EXA called me. It's a CFD software company. They said, we'd like to interview you. I said, I'm just about to accept a job. They said, well, if you haven't signed anything, then just come tomorrow. So they flew me out to Boston, interviewed me all day. And in the evening, the hiring manager said, don't accept that offer. We'll send you an offer. That was my sliding doors moment. It opened the door. Opened the door to this kind of career, which you see on the screen. And it could have been something quite different. So yeah, I'm forever grateful to my mentor at EXA, who gave me the first job. I learned a lot there. It was a CFD company where I started off. And I'll show you a few things at various points in my career that I did. But after EXA, I had this opportunity to go to McLaren in their automotive division. So McLaren was starting off a very early phase of designing road cars. And I joined them as initially a CFD engineer to develop the in-house CFD capability there. And I worked on a few road cars there. And then I went to Williams Advanced Engineering to work on another road car. And then I got the opportunity to jump to F1. And I spent good 10 years in F1, which was wonderful and torturous and everything that comes with it.
Yes, pretty much. So in a very funny way, like the career found you, didn't it? Like you want that focus that you want to get into F1 or motorsports. You were just looking for a curious challenge and something that was exciting, and you were kind of led into this way almost, which is very opposite to what my storyline is.
Yeah, it's interesting. I think everybody has different stories and how people get into this. But yeah, there was a moment which I'll talk about, which made me think I have to do this. I have to be in F1, and I'll tell you about it.
Yeah.
But at the moment, I work at Bentley Motors. I'm the aerodynamics technical manager in the company, and it is again automotive. So my F1 career spanned 10 years, but I'm back in the automotive fold.
Nice.
So just looking at a few interesting things throughout my career. So when I was at the CFD company, I very luckily again they sent me to work on NASCAR. So I used to go down to North Carolina. We worked with Toyota Camry at the time, and I helped develop their 2007 car, and that was my introduction to motorsports. And it was an interesting life, NASCAR, being with the team in North Carolina, and it gave me a bit of it was an appetizer almost. It was being in the wind tunnel there, being at the racetrack, and seeing how the world of motorsports worked. When I then moved to McLaren, I was very much focused on road cars. So these were the first two cars that McLaren released, and I was instrumental in the aerodynamics of these, especially the McLaren P1. That was a very cool project. I'm very proud of this car, and I was one of the aerodynamics engineers who worked on a lot of the aero components on this car. And it is a bit of a poster car in terms of hypercars. it's aged, but hopefully it's aged well. And then I went to Williams Advanced Engineering, worked on a Jaguar CX-75. Williams Advanced Engineering was contracted to develop this car with Jaguar, and it was a very cool project because initially it was supposed to have um, jet engines, basically tiny jet engines in the back. That was the concept, but it later sort of was slightly watered down and became a hybrid car, very powerful motors and engines. But it was again a very nice car. It never made it into production, but it did have its 15 minutes of fame, and that was playing the villain in a Bond movie. So the Jaguar CX-75 never saw production, but the prototypes were used in the Inspector, and it's in a chase scene in Rome. That's its 15 minutes of fame. I guess if you look it up, you'll see the a 4-minute chase sequence where the Jaguar CX-75 is driven by the villain and was chasing James Bond in an Aston Martin. But yeah, the moment that I talked about earlier, that I really wanted to get into F1, happened when I was at McLaren, and Lewis Hamilton won his first championship. There's a culture and at McLaren where when they win a race or the championship, everybody puts on the orange shirts. That's the winning shirt. And Lewis Hamilton came to the factory to say hello and shake hands with everybody, about 1,000 people at McLaren Technology Center. And you can see a slightly chubby version of me in the background there, next to Lewis, a very young Lewis, if I may say. He looks like a teenager. He's just out of his teens, actually, really, at that point. But yeah, this was the moment, the feeling and the emotions and everything, and it really wanted me to work in F1. It made me want to work in F1. So this was the moment that I really realized that I want this, and that changed the trajectory of my career a little bit, and I got into F1.
I think a lot of people on this webinar would like to know, Punith, if you've ever spoken to Lewis Hamilton, now actually Sir Lewis Hamilton now. So how was he like? I mean, pretty much he must have been during his teens, and Hamilton is a very changed personality nowadays. But how was he back then? Recall your first interaction with Lewis Hamilton.
So when he first joined McLaren, obviously he's just coming into the sport, coming up against Alonso, a world champion, and a very difficult competitor. And he actually rented a flat in Woking, and almost came in every day to work in a simulator, the gym, and interact with his race team, his mechanics. And I used to see him all the time, in the canteen especially. He was standing behind me one time in the canteen, and I did say hi. That was the only interaction, to be honest. And he was very, very down to earth and very willing to talk to people as and when his time allowed. And especially in those years, in the beginning, he was in the factory a lot. So yeah, he could see the determination. In the very first season, he was right on it, and I think it energized everybody in the team. I mean, I wasn't even directly involved, and I felt the energy, and I wanted to go into F1 straight away. So you can imagine the impact he had on the rest of the mechanics and the race team and the people developing the car.
Yeah, I say it's infectious, isn't it? Like once you start winning, it's very, very infectious. The energy, the momentum. I mean, I think it's a very underrated aspect of why winning teams keep winning, because it's just the momentum is with you. Everybody's in the right headspace and everybody wants to keep pushing, and the culture completely changes. So I believe this is one of the reasons why historically teams that win just like keep on winning. And I felt this at Red Bull, coming into a year 2021 when Red Bull was just, fighting against a superior Mercedes car, but the momentum was there. Everybody was really trying to push to try and, win that year because they wanted to break the fact that Mercedes had won everything in the hybrid era. And yeah, I remember the momentum. It was everybody was working until 8 p.m. Aero, vehicle dynamics, and everybody was pushing flat out. So yeah, for sure, I can imagine what you're saying.
Yeah, so that changed my career, and I spent the next 10 years in three different teams. Williams, where I spent most of my F1 career. I've worked in different departments in the aero department, different groups, different parts of the car. I've worked in the aero performance group, and maybe in another talk we can talk about aero department and then what people do. And it's just grown so much, and everybody has their role, and everybody has to do their best to do their job and everything. So it'll be interesting to do that as well. But I've been in a few different groups in an aero department. I was even sent to racetracks sometimes to sort of support the race team and the track aerodynamicist. That picture over there is from when we had a race in India. I was in the garage with Williams in India, and then I spent 7 years at Williams. I went from being an aerodynamicist to a senior aerodynamicist, and then I moved to Sauber in Switzerland. It was Alfa Romeo Sauber, and where I worked as the front car group leader. That was responsible for the development of the front of the car. And after a couple of years there, I came back to the UK and worked at AlphaTauri. That was my F1 career before I moved out again, and now back in automotive. I work at Bentley Motors and work on those kind of cool cars now.
Well, that's kind of laid the foundation as to who you are and what you've done, and I think we are all excited to hear about you demystifying the how F1 teams, including me, to be honest, how F1 teams tend to tend to simulate racetrack conditions in wind tunnels. So let's get into it. I know that you have 4 case studies to show. So we'll go over these 4 case studies, and I think the methodology we could focus is basically let's look at them from a very high level, because I know when we start talking aero, we just go on about it, and we'll try to keep some time to ask questions, because I can assume there'll be lots of questions. So guys, whoever, as you guys are preparing for your questions later, please try and infer to which particular case study you are asking a question about, depending on the 4 case studies. So this way, you guys also have to pay attention as to what you guys are asking for. Let's go for it.
Yeah, so let's jump into it. I think as Shubham mentioned, we will reserve some time for your questions. I've seen hands popping up already, and maybe the career path is also interesting. You can ask questions about it. It doesn't have to be only on the technical presentation. So if you just reserve that for towards the end, we'll get into all of that. So we'll talk about aerodynamics development tools that the engineers have at their disposal to make the race car faster. So I've just taken a few examples of race circuits. There's a few of my favorites, to be honest: Barcelona, Silverstone, Suzuka, and Brazil. It's just an example. And what do we see? What's the common theme? You've got straights, you've got corners, and those corners are all taken at different speeds. Some of them are very slow, some are very high speed. Some of them are in between the slow and high speeds. So let's just isolate the Barcelona circuit. It's almost a reference circuit for all the teams. If the car does well there, that means it's a well-rounded car. You see parts of the circuit where the car is power limited. Those are generally the straights. And you see the rest of the circuit where it's grip limited. So what that means is if you want to go faster, you need more grip. So the limitation is grip, and those are generally the corners. So the grip limited part of the track are the corners. The faster lap time is achieved by carrying more speed through corners. And what helps you achieve that is more grip through the tires. So the more the grip through the tires acting on the road, it helps you carry more speed into the corner and through the corner. And what gives you more grip? Aero gives you more grip, apart from all of the tire characteristics. If you assume all of that is equal, aerodynamics and downforce will give you more grip, it acting on the tires. And that's how you carry more speed and achieve a faster lap time. Let's look at Silverstone, one of my very, very favorite tracks. Also, it throws up a really interesting race most of the time because of the weather in UK. If you just look at this track, and I hope it's big enough on your screens, you can see all the different speed corners that I was referring to. So you've got high speed corners, medium speed corners, low speed corners. They're all at different, the car can take them at different speeds. Why do we need to treat them differently? All of these corners. It's because the car, as it goes through different speed corners, it's in a different attitude because of the downforce acting on the car, because of how the steering input that's demanded to navigate that corner, and also the ride height that is in a particular corner. So different speed corners, car tends to be in a different attitude. So that's why we need to treat them differently. Let's just quickly look at the British Grand Prix 2020 is just a very rough example. This corner 9. This is the one here. It's quite a high speed corner. And what I want to just illustrate here is the difference between a car, for example, Hamilton, who's right at the top end. He is probably one of the fastest drivers around that circuit in that qualifying session. He's carrying 301 kilometers per hour through this corner, while if you go right down there's Grosjean carrying 290. So there's a difference of 11 kilometers per hour. That's the speed difference that I'm talking about. The faster drivers are carrying through the corner. That was a high speed corner, so there are drivers taking this corner at 300 kilometers per hour. Now let's look at a very low speed corner. This is corner 4, which is lost my mouse. Yeah, corner 4, which is right here. It's a tight one here. The Silverstone this is just a guideline speed at which this corner is taken. It says 85, but of course, Formula 1 cars, Verstappen is taking it at 118 over here. And one of the slower ones in this particular thing was Latifi at 104. So again, huge difference between how much speed the drivers are carrying through that corner. That's what makes the difference. That's where the lap time comes from. And that's why we need to treat all of these corners differently while evaluating and developing a car aerodynamically. So what do we need to do? We need to add downforce in different types of corners: high speed, medium speed, and low speed. And how is this done? Well, there are entire aero departments dedicated to this pursuit. Lots of engineers focused on this methodology of testing, how to develop parts that make the car faster. So this is what we will talk about and look at a few details. So let's ask ourselves, how does an F1 aerodynamicist make the race car faster? What tools are available to an aerodynamics engineer? You've got the track, which is in a sense an ultimate tool because you're testing the real race car. Got the wind tunnel. You use a 60% scale model in a wind tunnel to test and develop the car. And then you've got CFD, which is a virtual environment. So you simulate the car with the CFD software, and you can develop that in this environment as well. And what we'll focus on today is the wind tunnel and some aspects of it. But as we lead into it, we need to ask a few interesting questions. So let's start with the track. As I said, it's the ultimate tool to develop a car because you're testing the race car that will be racing on that track or on a different track. But you've got the most realistic aspects, but it's very expensive. It's heavily restricted. in F1, as most of you know. It's very difficult to obtain force measurements because of all the noise with strain gauges and push rod loads, and it's quite a difficult measurement to make, the force measurements. There's also variability of conditions. So you might test something in the morning, you might test something in the evening, and the conditions have changed. So it's not very conducive to back-to-back testing when you're trying to improve the race car. The driver is in the loop because you need somebody to drive the car around the track, and that can also cause variations in testing. And it's very difficult to measure small improvements because of all these variations that I talked about. So it might be the most realistic environment, but it's very difficult to develop a car experimentally in this environment. So what do? We look at the wind tunnel. The wind tunnel is a very controlled testing environment. It's precise, very repeatable. Formula One teams spend a lot of money, a lot of time and effort to get their wind tunnels to be very repeatable, because all of the experimental accuracy depends on being able to repeat the model testing. And then you can get very accurate pressure and flow visualization measurements. You can get very good force measurements, and a lot of the things that were difficult to do on a track becomes easier in a wind tunnel because of the controlled environment. But the car in a wind tunnel has to really closely replicate the car behavior on track, because otherwise we're just not testing the right conditions, the right environment. And this is where we'll spend our time today, to talk about how Formula One teams really go to some extreme levels, or spend a lot of effort in trying to replicate those conditions, track conditions in the wind tunnel, so that they can test and develop the car accurately. Before we get technical, just thought I'll put this out here. Just ask myself, how many wind tunnels are capable of developing a modern F1 race car with all its efficient wind tunnel testing and all its model motion and all of the technology that's needed? And you can see there's a big bubble. Most F1 teams, as you expect, are in UK. So you've got Mercedes, Williams, Alpine, Red Bull, McLaren, and AlphaTauri wind tunnels here. There's Sauber in Switzerland. There's a Toyota wind tunnel, which some F1 teams were using until recently. That's very capable as well. And there's the Ferrari one in Italy. There are a few other wind tunnels, and obviously I might have missed some. Shubham might know a few more. There's the Dallara wind tunnel, which is capable of testing. There was a wind tunnel that a Spanish team owned, Epsilon Euskadi. I think the last I heard, it was dismantled, unfortunately, due to financial problems, but that was capable of running over Formula One car as well. And I've been fortunate and lucky enough to work in 4 of these wind tunnels. I worked at Williams, Sauber, AlphaTauri, and the Red Bull wind tunnel. Shubham, do you want to come in and do you know of any more?
No, I don't know of any more. Actually, I do know that there is a new one coming, or a new one being reworked around the Silverstone track for the new F1 teams that were trying. So they were trying on those ones. I don't know if it's I haven't been inside, but I don't know if they can do a full scale development and the kind of efficiency that's required for the repeatability that's required from a tunnel. And I remember when I used to be at Red Bull, like the repeatability was such an issue. And you've worked in the same tunnel, because it's the old World War II time level building, and temperature measurement and temperature control is so hard. So yeah, it's a challenge. But I've also seen the Dallara wind tunnel, and that I have to say I was very, very impressed with the Dallara wind tunnel facility. And yeah, it's all, like you could easily modify that to an F1 grade wind tunnel. I mean Haas used to use it for a long time for their aero development. But I would still say, like, comparing my time at Red Bull to Dallara, Red Bull's obviously was much more sophisticated, in tune with some of the processes that you need specifically for F1. I could just point out a huge performance difference between a Haas and a Red Bull F1 team, just looking at the wind tunnel development infrastructure, because yeah, Dallara had everything you needed for a motorsport company, and some bits for a something like a spec series like F2 Indy, but something that's really competitive, where you're starting to talk about tire shape in corners and all that kind of stuff. Nah, not really. That's where Red Bull used bespoken techniques in order to replicate racetrack conditions.
Yeah, that's what makes it more interesting. These tunnels are, I think you can modify a lot of tunnels around the world to be able to test a Formula One scale model, or even a full scale Formula One car in some cases. But doing it in such an efficient way to be able to develop the car is challenging, and all of the technology and some of it we'll speak about in the next few slides. That they're all very, very much developed by the teams. Good. So let's take this image as an example. It's a Sauber wind tunnel. I've worked here, and it's the model, not a very recent one. I think this one is the Formula One FOM model in the tunnel, and it's a good example to talk around. So there's some technology in the wind tunnel that's almost standard in all F1 wind tunnels. There's the model motion. So you've got this thing that holds the model, and the balance is connected to this, the force balance. It's a beautiful piece of equipment. It can control the model in many different ways. It can change the roll, the steer of the wheels, the ride height independently, front and rear ride heights. Then the wind tunnel turntable can change the yaw angle. So the model motion it can be whatever the car on the track will be. You can replicate that. And then you've got a fully articulated suspension. So you've got very realistic suspensions. They're set up to be as close to the real race car as well in terms of angles and everything. And that suspension allows the wheel to be fully articulated. We'll talk about that a little bit more when we come to the tires. There's a rolling road, which has a bit of texture to simulate the road roughness. Again, we'll talk about it in a bit more detail, why that's needed. This force measurement, like I mentioned, we've got the main balance that'll measure the 3 moments and 3 components of forces, but also a lot of teams tend to have strain gauges and independent force measurements in the front wing, the rear wing, and maybe even more that I haven't heard of from some other teams. It's flow measurement, which in a very controlled environment you can do flow measurement to your heart's content. You've got PIV in many wind tunnels. Sauber, I don't think this PIV, but they do have this arm here, which you can see. That's the Cobra probe, which will you can program it to go anywhere around the car and measure the flow field in slices. So you can measure the total pressure and whatever components. If you measure the velocity components, you can derive various other vorticity and other interesting features that an aero engineer would want to look at. So these are the standard things that most F1 teams will have, but there are lots of resources to understand all of this. I think through UMA, Willem, for example, Willem Toet he's got some very good videos describing all of this in detail. But what we'll do is we'll go a step further and look at some details. Before we go there, I just want to throw out a question to our audience. What materials do you think are used to make a Formula One scale model, wind tunnel scale model? For example, the one that showed in the image. If somebody wants to answer that, either in the chat.
3D printing. I mean, you guys can put it up in the chat. I'm looking at the chat for responses.
Yeah, go on. You can read
30
that out.
seconds, guys. Yeah. I mean, it'll be interesting to know the answer to this because I always thought of a certain answer. And when I was working at Delara, I realized, okay, things are a bit different to what I thought here. And it's very
And
interesting why they choose those specific materials, especially when it
it
comes to the front wing.
it might be different to the answers I've seen as well. So yeah,
Yeah. A
that's
lot
why
of
I just
people
go with the
are
middle.
responding by saying plastics, 3D printing, but 3D
Yeah.
printing is not a material, guys. 3D printing is a methodology.
Okay, let's go with, so it's a lot of answers about rapid prototyped materials, yeah. So
Yeah,
plastics, a lot of them. So
yeah,
that's true. So a lot of the model is made with 3D printed material, which is predominantly a lot of plastics, but the the spine of the model is metal, because you need a solid base. Wings have a metal spine as well, because you need to replicate a sort of a bending motion and everything, which I'll come to. There's also a reason they take a lot of load, incredible amounts of load. So I think the rigidity and the strength required is one of the factors. There's also carbon, because carbon is very strong, very light, and also when things get really small, then you'd rather use carbon because it has the strength that the 3D printed plastics don't give you. So those are the different materials that I know of. If you have
yeah.
anything to add.
No, I think from what I studied, obviously, because I haven't worked on. I mean, we used to work plastics. We used to have a spine, a metal spine at Red Bull, but there used to be a lot of the flaps and all those elements used to be a lot of plastics because they're cheap, they're
Yep.
quick, and they could be printed easily. And then you would use different materials when you would want to run like a baseline run or like an update car run.
Mhm.
That's when you would try to introduce factors such as you try to make more carbon parts. But when you're just using trying to switch between parts, which at least with parts that you would know would be used quite frequently or changed quite frequently, they were mostly plastics most of the time.
Yep.
And
Yep.
it's interesting, as you said, why the front wing needs to be of that material because you would expect uh, you're saying that front wing, and this is a question probably for the audience, and we should probably go into the next slide with this question is if the front wing takes so much load, then why shouldn't we make it out of carbon fiber? Makes sense, right? But
Yep.
not really, and we'll find out.
That is, yeah. So so as I said, we won't talk about the standard things that we can see in a wind tunnel today. What I want to spend my time talking about is some of the more detailed aspects that teams try to do to replicate the track conditions. And these are the four case studies that Shubham mentioned. So one will be the front wing deformation, which we just sort of briefly spoke about just now. The other is the belt, the rolling road, and the roughness of it, and why that's important. Then we'll speak about tire modeling, and then we'll look at some rear wing, some interesting aspects on that. So let's jump in straight away. So front wing deformation. Right, so this is just an image of an old F1 car in a wind tunnel with some technicians probably changing some parts. And for one material I forgot, Shubham, is tape.
Yeah.
You can
Yeah,
never have an F1 model without tape, I guess. How much ever you try, tape
yeah,
and wax.
tape and
Um,
wax.
so let's look at this front wing. What's happening here? So it's supported in the center over here, but the rest of the wing is unsupported. So it's almost like a cantilever held in the middle. The loading of the front wing, so there'll be a span-wise distribution. So when I say that, I mean the load in the y direction is not a constant load. There'll be a certain distribution of load, and that will lead to a bit of deflection, especially in these old generation wings. You've got all of this winglets popping out of everywhere in the outboard section. Loading here is very heavy, and it's supported here, so there'll be a bit of bending on the front wing. There is deflection of the nose related to the chassis, and there's deflection of the wing related to the nose. So there's two aspects of it. So that is a problem. So this is a problem that's faced by the aero engineer in the wind tunnel. So there's all of this deflection happening. And why is this important? Because the car on the racetrack sees this kind of deflection, and we need to replicate that if we're going to actually develop a front wing. That is the statement of the problem. What happens when the front wing deflects? The wing starts bending towards the ground, towards the floor. Imagine this: if this model was running on the floor, then it starts bending towards the floor. Downforce starts increasing up to a point before you eventually stall the car if you bend it too much. And also the flow structures, all of the aerodynamic flow structures associated with elements of the front wing, they start getting more loaded as it bends towards the floor. In some instances, that statement may not be true. It might be the opposite, but the point is that it changes. So that's why it's important to replicate this deflection in the wind tunnel. So what do teams do? This is the statement. So the front wing performance, if we want to measure it accurately in the wind tunnel, its deformation should really be replicated. So how do we do this? We go back to the racetrack because that's the real environment. We collect data from the racetrack for nose and front wing deflection, and that's done by putting a lot of laser measurement devices and markers on the front wing. So you run the car with lasers to be able to measure the deflections. You then validate your FE models from the track data. So you set up a FEA model of the front wing and use your track data to correlate your model, and that FE model becomes the basis of what you want to then do in this smaller scale model, the 60% scale model. So now you know how the racetrack, the wing is behaving on the racetrack because you've measured everything. You've created your FEA model as well. So now we need to replicate that in the wind tunnel, and it's a 60% scale model. So it's good that we've made our FEA model and we've correlated it. And we need a system now in the wind tunnel to be able to control this deflection. So what we do, what wind tunnel, a lot of teams do is they focus on the construction of the wing itself. So the foundation of the wing is metal. So there's a little bit of a bending and cantilever action like a real wing, and then the rest of it is controlled by this kind of a tether system. So this is just an example image just to talk around, but in the scale model, you obviously don't have this big towers. It's all done inside of the nose, but you have these kind of tethers that come out that hold the front wing, and that tether, when the front wing starts getting loaded, it's a certain material and a certain it has a certain deformation characteristic that helps you to replicate what you've seen on track.
Yeah, just to add on to that, Punith, I just want to tell all the participants how accurate these measurements need to be. Okay, because you're talking about slot gaps and deformations in millimeters, right? Like for you to be able to match it, and for you to set up to create a setup that matches what you want is extremely hard. And there's a lot of validation, a lot of effort put in by teams to make sure this happens. So before every run, there are heights being measured by people and being written on a sheet, so that engineers like me, when I see the data and I see everything green, and be like, okay, we've discovered some front wing performance. You go and see, all right, let's, my manager would say, can you please go and check, this looks a bit unrealistic, can you please go and check the sheet height setups? Because sometimes, like poor Alpha Tauri had to, I remember when you guys were, Alpha Tauri had to do all the night shifts and all the weekend shifts sometimes, compared to Red Bull. And it was the opposite before, and we used to always complain about it. But sometimes engineers, get it wrong, because an engineer from the rear team, for example, who doesn't have experience on working on the front wing, is working on the front wings, and he doesn't know all the small intricacies that you are playing with sometimes, and it becomes super super important and very very difficult to manage this. Actually, a lot of my time when I was at Red Bull was just spent on front wing deformation and correlation, because they had to get it right, because the new 2022 regulations had a different way of mounting the front wings, and the
Yeah.
entire structural system changed. So it
Yeah.
was very important to have new processes in play for the validation of the data that we were getting. So it's a super difficult job. It might look very simple, but it's not just difficult to get it right, but also difficult to keep track of it as you are developing the car.
And why is this important? Because the thing is, when you've designed a new version of a flap or an end plate of the front wing, and you think that'll give you more performance, you need to make sure that you've measured it against the correct baseline. If there was a mistake in the deformation of the front wing in the baseline, then you may not have actually measured the right thing. You think it's a positive step, but it may not. So keeping track of this, and this goes back to the repeatability of the model. It's an extremely complex model, and I always say that it's extremely complex experiment. Each run is an extremely complex experiment, and because of how efficient wind tunnel testing is, and the teams have developed it over the years, a lot of things are lost in, they're hidden. They happen in the background. But they do happen. It's a very complex test experiment, and everything is taken care to keep the baseline where it should be, and that should be perfect.
Absolutely.
So moving on, again, we were talking about it this very, very high level. We could probably spend an hour just talking about the front wing deformation system, but we won't do that today. The second thing I want to just touch upon is the belt, the rolling road, and the roughness that I mentioned. So when you look at this this belt here, it normally has a texture, a roughness like the tarmac asphalt on a road. And why is that? So let's look at what's happening. So there's something called ground plane loss. What happens is there's really highly accelerated flow under the front wing, between the front wing and the road, and boundary layer losses start building up in this region. And in the previous generation of wings, before the new regulations, there were lots of vortices that were being formed as well, and these vortices would make things worse. They would pick up this boundary layer loss and make it even bigger. So there is boundary layer loss happening, and what happens is if it becomes big and travels down the wing, it acts as a blockage to the flow coming under the wing, and that's why it's important to get that right. So this is something that real that happens in the racetrack, and we need to get that right in the wind tunnel. We need to be able to predict that blockage effect of this loss coming from the rough nature of the road, and we need to get it right so that we can then make the car faster with new front wings. So we know that we're measuring the right thing, and when we go back to the racetrack, it will perform as it's intended.
Yeah. I think a very interesting perspective is, I think the vortices that you're talking about were also, in the older regulations, you had the strakes, which were like super hard to get the combination of loading, which strake, how much do you load it, and those vortices that were shed off by the strakes would pick up the ground losses. But
Exactly.
very interesting perspective is now that all of that is gone.
It's gone, yeah.
Where this becomes really important are the strakes near at the entrance of the floor for the new regulation. And the entire floor, if you like, I have seen runs which say with texture, without texture, and the difference between these runs is huge. Right? Like if you've seen the PIV or not the PIV, sorry, the flow field and the numbers that you get, the static pressure probes. And that kind of, I think when somebody sees something like that, like a run with clean ground plane and one with textured ground plane, you really realize how much, what is, you question your repeatability, and you question sometimes your processes. You're like, damn, that's like 15% of downforce just gone. And this is why the devil lies in the detail a lot of the times, because who's to say that your texture is the right texture? And I think he's going to jump onto exactly that, the macro and the micro roughnesses.
Yeah, good leading question. So it's so what happens is every track, Pirelli as a tire supplier, they generally provide information on the roughness characteristics of a track, because it impacts the degradation of the tire and how the tire behaves and the life of the tire and everything. And those who watch races religiously and regularly, they know all about this. So the data is there. We get micro and macro roughness data. And what is micro and macro roughness? Macro roughness is basically the large scale perturbations in the surface, and micro roughness is the smaller, really small scale perturbation. Both are important. I think that's too much detail for today, but we get this data for all of the tracks. But how do you then decide what you're going to do in the wind tunnel? One of the ways, and maybe different teams do it a different way, is to kind of average across tracks, or you choose a very representative track like Barcelona. So there are different ways, but the ones I've seen is mostly averaged across the whole season in different tracks, and you come up with the roughness characteristics of the road that you want to try and replicate. And that texture then becomes your baseline and what you want to replicate in the scale model. But how do you know if you've got it right? That's the big question. So what do? We go back to the racetrack again. We look at the full size, the real car, and we measure things. So in the previous regulations, the key thing was to measure just behind the front wing. It might be quite different now, as Shubham just mentioned. So one way to do it is you put a rake, like this image shows in this car, just behind the front wing, and you measure the losses that are appearing due to this due to the roughness. And then you have an idea of what you're correlating your wind tunnel belt to. So then you come back to the wind tunnel, use different surface roughness, surface textures. You can get various roughness characteristics that you can stick on to the rolling road, and a lot of testing is done to get the right roughness so that you can correlate your losses to what you've observed from the racetrack. That's how I've seen this done, and it's quite an important one in the old regulations and in the new ones as well, for different reasons. Right, next topic would be tire modeling. So let's move on towards the tires. So what is so important about tires that happens on a racetrack that we need to be really careful about when we're testing in the wind tunnel? First of all, why is tire modeling so important? It's an open wheel race car that we're talking about, so the tires are exposed to flow, and everything that happens around it is very important. So the vortices that are sent towards the tire, the flow separation around the tire wake shape, everything is important because it impacts critical downstream components that you're trying to improve. So that front tire wake, for example, it impacts the rest of the car depending on how it behaves. So that's why it's very important. We need to control tire related flow structures in a very efficient way because we can gain lots of performance if it's done in the right way. That's why it's key. And one of the other very, very important aspects that you don't see. So in this image, for example, you see how exposed on a race car the tire is, and how important this wheel wake is, the vortices that are sent around the car. Another very important aspect is where the tire touches the floor. There's something called tire squish or squirt. Different teams call it in different ways, but where It's basically where the tire contacts the floor. There's a contact patch, and the flow around that behaves quite differently because it's a very squeezed region, and you get a lot of losses that squirt inboard from the inboard corner that affect the rest of the car. This, for example, is just a image showing the tire squirting into the diffuser and the rear diffuser in the old regulations. So these are the reasons why tire modeling is important. So we need to get tire modeling correct. We need to know how it's behaving on the racetrack, and we need to replicate that in the wind tunnel. So what is the methodology? We have to replicate a full size tire on a 60% model tire. So that's the challenge in front of us. And how do we do it? We start with take the full size tire and we characterize it. And what I mean by that is we need to know how it behaves in different conditions. We need to measure the contact patch and the sidewall shape and how it changes when you change force, camber, tire pressure, and different variables. So once you know how these two things are changing with all of these variables, you know how the tire behaves on the racetrack in the full size tire. And this is some of the ways to do it. You measure the contact patch on a tire static tire rig, which can be done. So again, we won't go into details. There's very simple technology with pressure mats and things like that. We can measure the contact patch, so you know how big or small the contact patch is as a function of force, downforce acting on the tire, as a function of camber, as a function of tire pressure. Then you can use lasers to measure the sidewall shape and how it changes. An F1 tire gets deformed massively because of the huge forces acting on it, especially in high-speed cornering. You've got the mechanical forces pulling the tire apart. You've got downforce pushing it down, and your sidewall deforms massively. So all of these are measured in this way. So you can actually do laser measurements on racetrack, which I've been involved in one of my stints in a team. Once you've done that, you know how the full size tire behaves. So then you can replicate that behavior in the wind tunnel on the smaller tire. But how is that done? It's not easy. It's not easy. You need a lot of technology to do that in the wind tunnel. So one of the technologies is to use active suspension. And what that means is your suspension here, you're able to control how much load is applied onto the tire so that you get the right deformation and the right contact patch shape. And another aspect is you have active tire pressure in the model. So you can control the tire pressure and hence control how the contact patch shape looks like. So these two are technologies that I know of that I used to control the contact patch and the shape of the tire, the sidewall. And all of this is done to replicate how the tire behaves on a racetrack for different corner speeds. So the kind of deformation that you see, it won't be the same for high speed corner or for a low speed corner. They'll be different. So when in the wind tunnel, you're testing different corner speeds, you need that to be changing. And that's why you have this technology to control how the tire is replicated in these different corner speeds.
Yeah, I think if I recollect another example of how important these tire pressures are, not the tire shape is. I think teams and you can question what is the repeatability of the shape that you're getting as well, huh? Because as the tire wears out, its deformation changes with time. So teams have set practices where they use certain runs just to check this periodically to make sure that there is not an error that's built up in their simulations or in their wind tunnel runs. So that's again another key aspect. It's just not again getting it right, but then consistently getting it right is the heart of it actually.
Yeah, I think there are other practices where you don't put a new tire onto the model. It's always done certain kilometers on a rig to be able to control and track, as you just mentioned, the baseline condition on how it's behaving. That's a very good point. Right. So before we go to the last topic, I just got another question for you. Imagine a wet race where it's raining heavily. What aspects of a car performance do you think are degraded the most when rain affects a race?
Okay, we're looking for the chat. Anyone has any suggestions? Grip, drag is increased, grip, cornering speeds. A lot of people saying grip.
So it's a good answer. So tire performance is massively degraded, as we all know. I think that's everybody speaks about it. It's a headline. But there are some other things which are happening in the background, which we'll go to. It was almost a leading end question for me, but that's the tire performance is a very dominant factor, tire temperature, etc. But let's look at some other things that may happen in rain. Let's look at a rear wing. So a Formula One rear wing is generally a two-element rear wing. It's highly loaded. It produces a lot of downforce. And when you put that rear wing in rain, what happens? Well, let's look at this image again. So imagine this rear wing in just normal dry conditions, and then you put the same rear wing in wet conditions, in heavy rain. You've got lots of droplets impinging on the leading edge and reflecting off it. That's affecting the incoming angle of attack of the flow. You've got a water film that forms on the suction side. So depending on how heavy the rain is, there's a film of water that starts building up on the suction side and traveling up the wing, and that film can be quite thick if it's very heavy rain. What happens is that film of water, it changes the effective shape of the wing. So you've designed this wing, but imagine adding a film of water with some thickness to it, and now you don't know what the shape of the wing is anymore. It depends on the film of water. There are also small rivulets and craters in the water film as the rain disperses and the water flows off the surface. You get all these rivulets and craters. And what that does is it can alter the surface roughness that the flow experiences. So because the flow is now not attached to the surface, it's flowing on the film of water. And that film of water has a different roughness characteristic to it. So it's completely changed. It's changed the environment that it's working in. And that is the interesting thing. So this is something that happens in racetrack. So how can we then replicate this in the wind tunnel? Some teams, what they do is they literally rain in the wind tunnel on the rear wing. So you've got a grid of spray nozzles, which is a rake of finely tuned nozzle diameter, because you need to tune the rain droplets and the density of the droplets to be able to match a certain level of rain, like an average level of rain, and not a hurricane. You would hope that you won't be racing in a hurricane, so you need to tune those droplet density and droplet size to work in a average rain condition, like sometimes we see in Japan or Suzuka or Spa, and that can be tuned by using laser sheets just in front of the wing. So you can take laser sheet measurements and look at the droplet size and the droplet density. And then once you've got that grid and you're spraying water at your rear wing, the rear wing can then be tested at different conditions, because the rear wing obviously is not performing just in a straight line. It has to perform in all kinds of car positions and car attitudes. So you test it in different pitch angles, different yaw angles, to understand its behavior in rain. So as a rough example, this is just made up data. Imagine you have a baseline rear wing design, and what this plot shows is rear wing downforce on the y-axis, and yaw angle on the x-axis. So you're doing a yaw sweep of the rear wing. And imagine your baseline wing is the orange one. You design a really good rear wing, which has even more downforce as the blue one. Works perfectly in dry conditions. But as you spray rain and you start going in different yaw conditions, you'll start seeing drop-offs because flow is separating because of all the characteristics that I mentioned in the previous slide. So this is what teams have to be wary about when they're designing wing profiles and things. It has to work in all conditions, and rain is one of those extreme conditions that you see on the racetrack. So yeah, that was the last case study for me. If there's anything you want to comment on, sure.
Yeah, I think this was something that when we discussed this for the first time, it was completely new for me because I had not actually participated in any of this kind of a rain study while I was there because yeah, I don't think we did this actively back at Red Bull. And so I don't know whether they did it while I was not there, or we just, your focus is on developing the car in 2022 and you don't think much about the rain. You just let Max Verstappen do his thing, going offline in the rain and just sending one down the outside. But yeah, this was very interesting case study for me, actually. This is where I learned a lot when we were having a discussion. So good one. We already have like 16 questions, so it's going to be a long Q&A, which is great, but we'll let you finish. I think there are a couple of slides
There's just
left.
a couple of slides more. One thing to say on this is one thing to add on this is that I don't think every team does this because there's different philosophies. I believe Red Bull never really pushed rear wing performance to the top level because they didn't need it, and they always had something in hand in terms of tuning the rear wing performance. So you didn't need to be right at the edge. What happens is when you have a rear wing right at the edge, that's when any conditions that alter on the racetrack, if you have a wing at the edge, then you might be in trouble. So it really depends on the philosophy. If there's confidence that there's margin and headroom in your design, then you may not be too worried about stress testing. Right, just to wrap up, so as an aerodynamicist, you've made sure that your scale model is behaving in a similar manner to the full-scale race car on the track, right? You've done all of these things that we talked about and more to replicate racetrack conditions in the wind tunnel. How do you then make the car faster? So when the car is cornering, various parameters are changing. The steer, roll, yaw, ride height, they're all changing. How do you add downforce effectively? You do that by mapping the aerodynamic performance of the car through various parts of its dynamic envelope. So the car can reach, it has a dynamic envelope in which it operates. So you need to test whatever performance you're trying to add in the entire envelope. And that's called mapping the car performance in different attitudes. And the way it's done is you map it in different corners, low speed corners, medium speed corners, high speed corners. And why is that? Because the car is in different attitudes in these corners. You do it, you also map it in various parts of the corner itself. So just take one high speed corner. The car is in different conditions as it goes through the corner itself. You've got turn in, slight braking and turn in, you're pitching forward, and then you hit the apex, and then you've got the exit conditions. So the car attitude is constantly changing as it goes through the corner. So that not only do we need to look at different speed corners, but even within the corner, there are different ways the car positions itself. Then we also map some straight line conditions because they are important to track, and also for some other conditions, which we can talk about in a more detailed manner some other time. Then also you look at variation of all the aero forces with different parameters like steer, roll, yaw, and ride height. They're also mapped. So this is the way you develop the performance of the car. So you do all this on your baseline car, and then you design something new you put it on the car and do all this again, and then you come out with something to evaluate whether it's better or not. And this is a very complex topic, error mapping. It's something for another time, and hopefully we will talk about this in the future.
Yeah, we're planning to kind of curate a course in which basically we start going into these details more and more. Well, yeah, that's kind of all for the session. We're gonna jump on to Q&As, and for all the wonderful 15 questions, some of which we have responded to. We have Jagdish online as well, and there is something special coming your way. We would all like all of you all to, if some of you guys are joining in from your laptop, scan that QR code. And for people who are not sign in to your laptop, I'll drop the link to the I would say interest form or the feedback form in the chat. Now, what this is going to be really interesting. Before we jump onto the Q&A, is we are going to create we're going to host, like, the next step of UMA is to do a F1 data analysis workshop. A lot of people love the data analysis because there's so many YouTubers, ex-F1 guys who are trying and putting out some data analysis, but there are so many intricacies that are missed. So I think one of the first things that we wanted to do was we wanted to create a course in which we start explaining some of the details of modeling, of tire modeling, of data analysis, of telemetry, data cleaning, and also stuff like machine learning and AI being used in the data analysis field recently. So a lot of you guys who are interested in this area, fill up the feedback form, use the link in the chat or the barcode on the screen, and let us know if you are interested in something like this, because we will arrange a dedicated in-depth 8-hour workshop so that we can have you over a weekend and you can learn things in detail and also model things in detail. And we're planning to do something like this with Punith too. So, but that's going to be a separate communication. So let's jump on to the Q&A. I think I have an option of just popping the question here. So let's go live. Let's say answer live. Would you like to answer this question live? Do you see the Q&As, Punith?
Let me see. Yeah, there's lots. Yes, I can.
Yeah, so I think we can start from the first question from Joanne. Sorry, I just said answer to that question, but the question was how do teams replicate something like a Zandvoort, the camber at Zandvoort in wind tunnels? It's an interesting question because I had this one too when I was at Red Bull. So, but yeah, I'll let you go. How do teams first of all actually account for such extreme camber, because it's one small part of the track on one circuit in an entire season, right? So the question is of relevance more than anything else. But if teams wanted to, would they do it?
It's a difficult thing to do, isn't it? You've got control over camber in a wind tunnel model, but to actually look at the track camber is a difficult thing. You can do it in CFD. It's not difficult at all. And if there is sensitivity, then maybe teams would like to pursue that.
Okay. All right, let's jump on to the more question. I think more weight is required at the front, so more downforce required. I think I'll answer that question separately, but we'll go to the question. So by anonymous attendee, does the front wing deform more in the wind tunnel or on track? What does the tether do subsequently?
So the idea is to match how it's deforming on the track with the tether system. So you can control the tension in the tether and the material of the tether, so that you can control how much it deforms and replicate exactly what it's doing on the racetrack. That's why we take all the measurements from the racetrack and we try to model that behavior in the wind tunnel. And it's done. There are lots of tests happening in the background normally on a reference model. So most teams have a reference model that they do the research on. It's not a development model. You're not making the car faster with on that model, but you're introducing technology and research by doing all the work on this model. So they develop this kind of tether technology on this reference model or a research model, and then it's then introduced onto the live production scale model normally.
Absolutely. Well, we have a question from Leonardo. So when you are developing a new part, how do you decide which texture to use? Because there is one for every track. I think you kind of answered this question, but you can
Yeah.
quickly go over it.
Yeah, it's a difficult one. It's just you can what I've seen is that you average across the season, and you develop your car so that it behaves across the season in a certain way, and you have confidence that you're doing the right thing for a lot of racetracks and not just a specific one.
Yeah. Okay, this is a very fundamental question, but I know that we have people who are not aerodynamicists on this chat. But Alston asks, let's say if I want to test how the car behaves at 300 kilometers an hour, so is it tested at 300 kilometers an hour in the wind tunnel, or the speed is much lower due to the 60% scale models?
Yes, so it is a fundamental aero question. So to replicate what we need to do in the wind tunnel is to match something called Reynolds number. So you've got Reynolds number is basically a function of it's function of speed and viscosity of the air and things like that. So you try to match the Reynolds number of the racetrack in the wind tunnel, and because in the wind tunnel the scale model is smaller than a full size car, that means in general you need to increase the speed that you're running at to be able to match the aerodynamic flow structures and the behavior on the racetrack.
Yeah. So Alston, do read into something called as a Reynolds number, and I think that should answer your question. Ramesh
So
asks an interesting question.
sorry, one quick one. It's actually very good question. So you do two things. You have to match the Reynolds number to match the flow characteristics between racetrack and scale model. Then the other thing you need to really match is geometric accuracy. So those are the two things that you have to remember. Geometrically, the car has to be exactly the same, which is almost intuitive. You'd say yes,
Yeah.
everybody understands that. Reynolds number is a tricky one, so yeah, you'd have to do some reading on that.
Yeah. Well, Ramesh asks a relevant question. I think he says, isn't all these things, like the front wing tethers, the main I don't know, sling that they call it that holds the model, aren't these like intrusive? And
Yeah.
And if they are, and aren't these intrusive devices that affect performance? So yeah.
Yeah, so especially with the tether, Ramesh, the image I showed is just something to talk around. So it's a lot more well designed than that. You don't have these towers sticking out. It's all done inside the nose, so there is no difference to the race car. Yes, the tethers stick out, but those are tiny cylinders, and the intrusion that they provide is negligible.
Yeah, and also the intrusion they provide is on the upper half, which is not really
It's the
doing
pressure
where the
side.
flow
Yeah.
physics. Yeah, it's the pressure side. Well, we have an interesting question from Priyanshu, which says, is it safe to use DRS during the rains, and why do they disable DRS?
It's an interesting question. So there's sometimes they've been it's difficult to get data when obviously not inside an F1 team, and there's one aspect where there's the DRS, so the flap opens up, but what's happening when it starts closing back, the flow attachment reattachment is critical to then suddenly get the performance back as you go to the end of the straight, and then you're going into the next corner. And that in rain, I think that can be affected, that there might be a delay in reattachment, and that could be quite dangerous.
Yeah. Okay, so this is an interesting question again. It says, we spoke about the rain and about the rear wing, but what about the effect of the rain on the front wing?
Yeah, I haven't seen such. I've never designed front wings that were so stressed that you'd have to consider a small change in characteristic of a rain, what rain does to a front wing. So it's normally because of the way the front wing operates, it does more than just generate downforce. It does a lot of things. It manages flow around the tires. It manages flow to the floor. It does so many other things than just simply generate downforce. So, and it operates in a very different environment, close to the ground as well. So it's quite different. The design of it is quite different to the rear wing, and
Yeah,
I've
there's more
never.
complexities involved, and when you are kind of studying this kind of a problem, you want to isolate the complexity in a way almost. So I think that's why the rear wing would be a good choice. But front wings would be very hard to characterize, just to answer the question. Very, very difficult to characterize. Well, moving slightly away from the theme of technical bits, I think Krutarth asks a nice question like, can you recommend a few exercises for designing how to grow in the field of designing aerodynamics?
Yeah, so I think there are skills that you need, which Shubham has talked about in his own posts and videos, and there's a lot of talk of upskilling and to be an aerodynamics engineer in an F1 team, you need some skills in CAD that that'll allow you to design what you want. But then it's also a lot of knowledge about simulation and experimental aerodynamics, and that's where I think the focus should be. So the design part is, yes, you can work on it with some CAD packages and surfacing skills, but I think the fundamental to be an aero engineer is really understanding the details of the simulation world and the experimental world.
Well, good news is if you guys fill up the forms that the link is put up to, we will get in touch with you for signing up for new courses that we're going to host by Punith, by William, and even by people who design who are now designing cars in F1. So there's all stuff is work in progress, but we need to know that you guys are interested in it. So please fill up the forms or use the link so that you guys register your interests, and then we kind of push these courses out as soon as possible because of the high interest generated on these courses. All right, so that one's done. I am current. Okay, what are the chances of a master's degree in sport engineering? So that will get back to your question. While scaling the model, do we consider all three similarities? Yes, we do, as much as we can. Are there other wind tunnels used to validate CFD results? Okay, so this one's nice actually. Let's talk a little bit about, so Aditya asks about, are the wind tunnel results used to validate the CFD results or the other way around?
Yeah, interesting question. It really depends on the philosophy as teams. Red Bull, I think they have their own philosophy, which until recently was not really matched by any other team. There are certain teams that use the wind tunnel as a primary tool, and CFD is only is almost a selection. So you filter parts that you send to the wind tunnel, but the ultimate selection happens in the wind tunnel. That's what a lot of teams used to follow, that kind of philosophy. Some teams, they use both tools as independent tools to develop the race car, because there's something called curved flow, which I probably shouldn't have mentioned, but it opens a can of worms.
Yeah.
Because the reality is that when a car goes around the corner, you're not sliding through the corner like some sort of drift car. You are actually going around the corner. So this curved flow, and not sliding through the corner. So curved flow is a very difficult thing to do in a wind tunnel, but you can do it in CFD. So the team philosophy depends on what you're trying to do. If you're using them as independent tools to directly develop the race car, then you can take advantage of some things that can be done in experimental world, and some things that can't be done there, and some things that are very easy to do in CFD. But there are some limitations in CFD because of the turbulence modeling and all of the things that come with it.
Nice. Well, Siddharth asked a question which I'm going to take. It's like I'm currently pursuing my bachelor's in aerospace engineering and I'm in my first year. I'm a bachelor in aerospace engineer myself. What kind of courses should I do and what kind of competition should I participate in to increase my chances of getting in an internship and finally a chance at a master's degree in motorsport engineering? So that for young enthusiasts like you, this is what UMA is bringing basically. We are going to curate courses by using the expertise of people like Punith himself, but in all different areas of motorsports, so that we can deliver you courses from world-class experts, and then UMA can then provide you some kind of an internship. We already had a successful Lime program, and 24 of our students are currently working with the Indian F4 Championship in the pits, working alongside as assistants to race engineers and race mechanics from MP Motorsports, which is the Formula 2 team. So we already have success stories building up, and we are already creating a new talent pool in India of motorsport engineering. So join us in our venture, and hopefully we'll be able to propel your career. All right, now that I've done the marketing bit, let's go. Let's get some bit of aero into our heads again. To what level is the surface texture and roughness of the real car replicated on the scale model? Mrugang. Mrugang, by the way, is one of our Lime students and a really smart guy, by the way. So shout out, go for it.
So I believe he's talking about surface roughness on the body and parts of the
Yeah,
scale model.
yeah.
So the race car obviously has a painted finish, and the scale model parts are quite carefully painted as well. The plastic materials that are used are not just tested, generally not tested straight away in that condition. It's always there's a consistent paint finish applied to them so that you don't get lost in the differences between surface roughness and texture.
Wow. I don't think we used to paint stuff at Red Bull, but yeah.
Well,
I think
what I've seen is what I've seen a lot of everything was consistent with painted parts.
yeah.
Interesting that you mentioned that.
Yeah, I don't think so. I don't remember. I think people are just in such a rush that they didn't really have time to paint it. They would, ideally, as you mentioned, but I think there was so much, I think parts were reaching just before the test, so nobody
Mm.
had time to paint anything. But they did make sure that the 3D printing finish was very consistent, and they would basically kind of sandpaper the whole thing to make sure that there was a consistency. That for sure happened. Is there any procedural or AI generation when developing new car pieces? I don't know. I don't know if you've been involved in any AI bits for car development.
No,
Yeah,
no, I can't
neither
say
have
I've.
I, but I know some teams are using it. Um, Chandan Singh Patel, why don't we use hydrographic material to do the thin layer paint all over the rear wings to reduce problem from rainfall? Interesting.
Sorry, could you repeat that?
Why don't we use hydrographic, but I think it's hydrophobic material or
Yeah.
graphic material to do a thin layer of paint all over
Hmm.
the rear wings to reduce the problem from rainfall?
Yeah. So that's one of the mitigation ideas. So either you create a certain roughness that allows water, basically emptying the water film. So you create channels for that to happen, like you have on the tires with the grooves and stuff. But that only can only do that much. If it's just very heavy rain and very thick film, then I think you can start looking at hydrophobic coatings and things like that, which you see on normal road cars and stuff, on windscreens and other areas that need to be water managed to be safe.
Yeah.
Yeah, definitely. Yeah.
Yeah. And I also think that you need to ask yourself about the weight of that paint. Like, do you want to carry that weight all the time? But maybe wherever you see a high probability, who knows? But I think, we've seen teams stop painting their cars to get into the weight limits, and you
Yeah.
see a lot of exposed carbon fiber. So you can imagine that also becomes a
Mm.
big but it might be interesting. Uh, maybe the performance in having consistency is more than the performance in the rain, especially is more than maybe the benefits outweigh the challenges, especially if you specifically know it's going to rain and just spray paint something, Rugang, again, an interesting question, and I think this was would address a larger audience. By increasing the velocity to match the Reynolds number, the flow might move to higher band of subsonic region, which is difficult to produce in the wind tunnel. How do you tackle that?
Yeah, it's once you're getting to the realms of the really high speed, like 300 kilometers per hour and stuff, that's quite difficult to achieve in the wind tunnel, and you're getting into very low levels of compressibility effects. Maybe probably not quite there, but I think definitely if you're hitting 400, 450, then compressibility becomes a factor as well. Yeah, I don't know what the answer is. The wind tunnel has a limitation, the fan speed and mechanical limitations around cooling and control systems. So different tunnels might be able to do different speeds.
Yeah,
as a
true.
maximum.
Yeah, that's very true. And also, I think you don't really want. I think the behavior of the car, the max you try is the high speed, which is around 250 kilometers an hour, because that's where things are changing. But the behavior of the car in a straight line at 300 or 350 is pretty much going to be the same. So teams don't test the maximum speed of the race car. They're more interested in pretty much a limitation is what is your high speed corner point or your testing point for high speed. What is the speed? What are the attitudes of the car? And that again is a different conversation altogether. How you develop the aero map. We'll do something for that as well. Um, how okay? How does perform? Okay, so because it's a famous question, let's go for it. How do porpoising, sorry, affect the performance of the car, and what causes porpoising, and what about the flexi wing? So basically, I think he's trying to connect the relationship between porpoising and flexi wings.
The porpoising is not something that I've delved into too much. So it's more in the era that you would have worked in, Shivam. So I
Yeah,
can
I
take the
mean,
other part of the question.
yeah, I think, for example, at Red Bull, we had like established methods to try and, after we saw it was a problem, we had like established methods in place, like every other team was developing. I can't comment about it on much, obviously. But for example, the front wing was not affected much because with the new regulations, the front wing was supposed to be so much higher, right? Which is one of the reasons why you lost so much front end of the car. So of course, if your car starts porpoising, then it induces a mode which changes when that vibrational mode is ignited in a way, your car will start flexing, but that is again not something that you would design your car for in the first place. So it does affect it, but it's not something that you would sit down and break your head. You would rather fix the porpoising first and develop your front wing independently.
It's a very good question where it came from, because we take care about front wing deformation and trying to replicate it, but this porpoising thing came as a bit of a shock to a lot of teams, and maybe a lot of the floor deformation and bending and deflection wasn't really looked at, and then some of that is coming from that floor edge, isn't it? It's deforming and closing off the gap and opening up as it goes through different modes.
Absolutely. Which is in a different, so it throws a whole aeroelasticity conversation altogether.
Yeah.
Another interesting question: has the new wheel winglets been that effective in controlling tire wake?
Is it I would imagine the top of the wake?
Yeah, I think the ones that's above the tire, the top of the wake, correct?
Yeah, that's quite effective at controlling the top of the wake, isn't it? Which as the regulations changed, and some of those outboard winglets were removed, and that we lost control of the top of the wake through those little vortices from those little winglets, and this is probably a replacement for that.
Yeah. Okay, there are so many more questions, but I think we've kind of exceeded the time. I'm just skimming through some questions. Uh, if there's something super interesting. How do you go about modeling factors? Okay. Yeah, this is an interesting question, a CFD question nonetheless, but I'm going to kind of get around it. So, how do you go about modeling factors like roughness and water film in CFD? So if you want to test this in CFD, how do you go about that?
So roughness is not difficult to do. So the most safety softwares will have a roughness characteristic that you can input into the surface characteristic, and it can also be done in a different way where you control the boundary layer growth profile. So it's a different way of doing roughness. So you have different abilities depending on the software.
Okay, all right. I think we'll wrap this session up. Thank you everyone for showing up. I think we've got we've got 31 open questions. So sorry we couldn't get through all of them. I think we already buzzed through 33 questions, which is, I've not gone through so many questions to be honest. So thank you for the warm response. We'll make sure we do something like this again so that you guys can show up and ask your questions again, because we have Christmas time and hopefully it's not as, we can find some time with some more experts to kind of go over this question. So thank you for showing up, and yeah, see y'all again. Make sure you finish the feedback form and the interest form in order to get signed up for new webinars and new courses coming up. Thank you, everyone. Have a good one. Thank you, Punith, for your time, and looking forward to hosting more courses and webinars with you.
Yeah, thank you very much. Thanks everyone. Bye.